Okay, welcome
Yeah, I
back
can play that
to lecture number 4
Yep.
of Gregory, Soyez, exploring high energy physics with jets. Please.
Okay, so thanks for coming then. It's all right. So what we did last week was to essentially get into the basic ideas of jet substructure, saying that the idea is to well, multifold, but mostly the part I concentrated on was trying to tag boosted objects. So whether a jet, if you have a high energy jet, where the decay product of whatever heavy object you have end up in a single jet, you need to be able to look at the internal dynamic of the internal kinematics of the jet in order to disentangle different types of jet that you can have. So I presented at the end of the lecture a series of methods, and this was only the tip of the iceberg. I presented only the ones I'm going to potentially discuss this week and next week. One of the things you may want to do, so there's about something like, say, 20 methods available, each of them with different parameters. One thing that people have tried to do after listing the methods is also combining them. And as we've seen, for example, as you can guess, combining something which tries to look for hard structure in your jet with something that constrains the soft radiation in the jet tends to give, since they work on two different concepts, combining two things like that tends to give a better performance. And this is what most of the experiments are doing now. So the other thing is, how do you test this? So in practice, you have a bunch of methods. What do you do to decide whether you want to use this or that method? And so the typical strategy at the beginning was essentially to use Monte Carlo generators. So you're in Pythia, you're in Hurwitz, you're in Sherpa, and you try to see whether whether Pythia and Hurwitz agree one with the other, so that your method is reasonably under control, and two, whether Pythia and Sherpa pass through, or Hurwitz and Sherpa pass through detector simulation, agree with what you see in the data, so at least you know that what you see in the data is reasonably well modeled by what you think is a good description of the physics. And once you have this, you can just ask the question, among the different methods I use, imagine I want to tag for, I don't know, for a BSM search, I want to search for a boosted W at 1 TV, then you can start looking whether which of the methods you have in your tool set is going to give you the best performance, okay? Now, there's about 20 methods. You can imagine making combinations of, at some point people trying to do combinations of any pairs of them. And they put this in a big plot. I wanted to show the plot, but since I had issues, I'll try to show it next week. If you have something like 20 methods, and you may pick up any pair, sometimes with different parameters, like soft drop beta equals 0, 1, and 2, and 4, at the end of the day, you get a plot which has hundreds of curves on it, and it's hard to see exactly what's going on in this kind of situation. So something like about 5 years ago, people started to ask the question whether there's any chance of trying to see through this based on a more fundamental approach. And this is essentially what I want to do today. So this lecture is essentially about substructure in QCD. Essentially perturbative QCD in this context. So the idea is there a way to have some QCD understanding of what's going on with these techniques, all right? So this will heavily use, again, pros and cons of this approach. It's perturbative QCD, so you don't really have access to what happens non-perturbatively, although I'll try to say a few words about this. It may have the advantage that it gives you some insight about what's going on versus running Monte Carlo, which can be viewed as a black box. So that's really what I'm going to focus on in this lecture. It may be seen as having the advantage that once you have a calculation, you can vary the parameters easily. Okay, you can vary the PT of the jet, you can vary the radius of the jet, you can vary the parameters in your tagger. Once you have a formula, varying parameters is easy. With a Monte Carlo, you'll have to rerun the Monte Carlo for each value of the parameters and so on and so forth. So it may that may be an advantage of this method. Now, again, there's the question of the precision of the perturbative calculation, and we'll go back to this. So the main idea is to use what we had 2 weeks ago, use the techniques, that QCD calculation techniques we developed, we reviewed 2 weeks ago, and try to see what you can say about these different techniques. So the first thing is the typical use case we're having is boosted jets. And in the case of boosted jets, take the case, I don't know, boosted W versus QCD background. The PT is much larger than the mass. And so automatically, these parameter rho that I had defined as being m squared over PD squared R squared, there's probably factors of R that you can fit in everywhere, becomes much smaller than 1. And so this means that naturally speaking, essentially by definition of what you mean by a boosted jet, you put yourself in a limit where you'd expect resummation calculations to be relevant. Okay? So this means that in turn, if you want to get the physics, the understanding of what the methods are doing, you're going to work at leading log accuracy. I'll try to discuss what's behind leading log accuracy and so on and so forth, especially for the amplitude people. But essentially that's what I'm going to do. Try to see first the easy leading log calculations, whether they can be applied to substructure, the first question is, can they be applied? It's not guaranteed, right? You're actually just trying to, you hit your jet quite hard. You make all sorts of fancy construction with it. It's not even guaranteed that such a calculation is at all doable. Actually, the prejudice initially was that doing substructure was actually equivalent to throwing away any hope of doing things in perturbative QCD. And it's been proven wrong since, but that was not trivial in the first place. So that's essentially what I'm going to focus on. Trying to see what we can say, what we can understand on these methods. And I'm going to consider 2 cases. The first one is quark versus gluon. And the second case is the case of, I would say, prong or groomers, prong finders. So let me try to follow again what I had prepared. For once, I prepared my lecture notes earlier in the week, so I can't remember what I decided to do earlier in the week. So let me review just, I'll use that all the way through the lectures. Let me review, remind you what we did 2 years ago in this context, and I'll try to put this somewhere so we can save it for the rest of the lectures. So 2 weeks ago we did the jet mass essentially, and what we had was, if you try to measure 1 over sigma d sigma d rho, and again rho being this variable here, or typically this can be generalized to any, well, to a whole bunch of observables that we call them V. Instead of measuring this, what you would typically want to do is the cumulative distribution, which integrates from 0 to some cut. Let me make a V or V. So that would be V prime, V prime. So that's the cumulative distribution instead of just the differential distribution. And we've seen that this, in many cases, and actually we'll discuss this, under some assumptions, this can be written as an exponential of R being a radiator. And I apologize already now. I'm using 2 different capital R. One stands for the jet radius. The other one stands for people call it a radiator, essentially because that's obtained from the radiation of one gluon. So there's an integration d theta squared over theta squared. As you see, usually angles scale with the jet radius, so I might sometimes, I'm used to do that when I do calculation on my own, just naively rescale the angle by R. I try to keep the radius dependence explicit, but I may fail at some point. There's an integration over the splitting function. There's an alpha s, which in principle depends on some scale. And then typically what you do is you impose that the V that you would calculate for a given value of an emission Let me call V1 because that would correspond to just a single emission at an angle theta with a momentum fraction z, has to be bigger than the external, that's R. So what this essentially corresponds to is your V1. I'll try to draw things in, as I told you, in the Lund plane, which is the plane where I put log 1 over theta in this axis, log z theta in this axis, so this corresponds to z equals 1. And so usually if this value of V1 corresponding to V gives you some, this is a line of equal V in this plane, essentially what this exponential means is that you veto real emissions in this region, essentially because they would give you too big a value of the observable. And so in this case, you only have virtual corrections. Real emissions are vetoed, real virtual emissions survive. In these regions, real and virtual cancel against each other, and so you only have an exponential of the virtual emissions above, which corresponds to this expression. And again, at leading log, P of z is just 2CR, depending on the flavor over z. And this gives you a collinear log and a soft log. So far, so good? So there's probably one other thing that I will need.
Can you write a little bit larger? Maybe it's only me, but no.
Okay.
Okay.
Yeah, good. Yeah. So there's another thing I'd like to emphasize. So once you have this, the cumulative distribution is just a derivative of this, so that's something everyone can easily do. One thing I like to do, and then I'll move on to the task at hand, is discuss again some, and I'll need that in the future, so that's bigger. I'm again going to I'm going to use this representation a lot. And one of the ideas, so has anyone met the Lund plane before? So the idea is that basically an emission like this has 2 degrees of freedom. One is so you can view this, imagine you have a dipole. That's actually something which is used in all Monte Carlos. Imagine you have a dipole, and in the rest frame of the dipole, this dipole would be back to back. A soft emission has essentially 2 degrees of freedom in this context. One is the kT, the impulsion, the momentum transverse the beam, and the other one is how close it is in the longitudinal coordinate. And so the longitudinal coordinate in this context is again rapidity, which is log. It's log. In principle, it's 1/2. It's minus log tangent theta over 2. 1/2 log tangent theta. And in this context, where the angle is small, this is just log 1 over theta. Okay. So what I'm doing here, in principle, you can write here really the rapidity along these beams, so log the tangent of the angle, and that would essentially give you a plane for the emission which extends both ways. So rapidity in one direction, log kT in the other direction, and this is just a kinematic limit that the energy of this emission is smaller than the energy of the emitter, the center of mass energy of the collision. What essentially I'm doing here is looking at a jet somewhere along one of these guys, and so I'm looking, if you wish, at just a slice in this plane. So this kind of construction was extensively used in developing Monte Carlos, because Monte Carlos, Parent shower Monte Carlos, tend to have to write emissions based on dipoles, and so this is a natural way to try and describe how Monte Carlo works. And by extension, it's also a natural way to try and discuss how resummation works. And as long as you work at leading log, you can almost do all the work based on these kind of cartoons without even referring to, and then once you have this drawing, there's an obvious correspondence in terms of expression. So I tend to find it a little bit more visual, and so maybe a little bit easier to discuss. So what happens in this case is another advantage of this is you can sort of view where the different physics in regions are. So typically the bulk of this plane here is the region which is soft and collinear. The region which is somewhere close to here, that's the region which is hard and collinear. So this would be double log, one log for soft, one log for collinear. If you start looking close to the edge there, you have a single log which is collinear. If you start looking close to this region there, you'll have soft and large angle. And if you have a given observable like this, if you start looking close to this region here, that's the region where multiple emissions are going to be single log and important. If you look somewhere deep down here, that's z times theta. Alpha s runs with z times theta as well. That's kt. Generally, kt is z times theta. So at some point, this is the hadronization region. That's where non-perturbative hadronization is going to happen. And similarly, if you have some soft radiation, which is at the same time soft and at large angle, like the underlying event, you get something which lives in this corner. So in this corner, somewhere here, you'll have the underlying event, or pile up if you insist. So essentially, this plane, visually speaking, you can sort of see, depending on where you start putting this cut, how you expect to be sensitive to all these arguments. And so that's something I'm going to use just to argue about what kind of behavior you should expect. That's something I'm going to use throughout this lecture. So this is the leading log would correspond to this. On top of the leading log, we've seen that you have a bunch of things. You have hard collinear. So in the hope to go to the next leading log, you'll have hard collinear emissions. I didn't discuss the constraint on this. Essentially, the constraint on this is that if you reserve a bunch of emissions, all these emissions at leading log can be treated as independent. And again, that means that you need to be able to, if you have n emissions building up V, you need to be able to write it down as saying there's only one that contributes. But we'll come back on this later. So the collinear, this is something which is fairly easy. That's essentially taking into account the splitting function there. You have the soft and large angle. This one we've seen is more complicated because any dipole in the event can radiate. So unless you have very simple topologies, like 2 or 3 legs in the final states, the minute you start building more complex events, like even 2 to 2 starts becoming more complex, this has a nasty color structure, and so this becomes more complicated and process dependent, while this is essentially universal. You'll have multiple emissions, and multiple emissions tend to be simple as long as you work with additive or max observables. They can be more complicated for more complicated observables. And you have non-global logs and clustering log. So this is essentially easy. This is essentially more or less easy. This is harder. And this is hard. Okay, so we'll keep this in mind in terms of discussing the physics later. So that's what I need from what we did in the past. So now, let me discuss quark versus gluon. Hey, Carlos, you asked about quark versus gluon. I promised you will answer your questions. Here we go.
Okay.
So if you talk to quark versus gluon jets, to anyone doing QCD, is probably going to be mad at you. Because that's ill-defined. Okay? A parton, when we discussed jets, I told you a jet is actually a well-defined parton. So the idea of a jet being a parton is something which is purely conceptual. It doesn't hold in terms of pure QCD, because a parton is not probably well-defined in QCD. You can have all sorts of splittings at any order, at a given order in perturbation theory that violates this quark versus parton. However, so in a way, when I say this, there's a big red flashing warning sign somewhere at the back of your mind that you should keep in mind, that this has to be taken with a grain of salt. There's no such thing as a quark or a gluon jet per se, in terms of a quark being just one quark and a gluon being just one gluon, okay? So, in a way, there's different ways to define quark and gluon jets. One, and they essentially can be ranked from well-defined to ill-defined, and typically saying it's a quark or a gluon parton saying it's a quark or a gluon parton, that's ill-defined. You can try to address things a bit more precisely, saying it's a quark or a gluon parton at Born level, and that's typically what you have in mind, okay? That the Born level description, I don't know, take a SUSY decay chain at some point, that might be when you think about the physics that's happening, you say this is going to decay into a quark or a gluon, and that's what you mean by quark and gluon jet in the end. Now again, this is ill-defined. There's no way that you can match this by an experimental measurement. So you can then say, well, hold on, and I understand that in all these kinds of languages this is still well-defined, right? Well, if you take the collinear limit, whatever happens is that you're going to emit some gluons, and so the flavor of my leading parton is not going to change, okay? Again, this is going to break at some point if you go high enough in logs, or if you start going to higher orders in whichever way. So at the end of the day, you can try to define things properly by saying at the end of the day, what I'm going to do is make a measurement. I'm going to measure something, sum-observable, well-defined, infrared and collinear safe, perfectly suited for both calculations in QCD and measurements in experiment. And the hope is that in a view which is biased and incorrect, but is just conceptual, the sample you get at the end is enhanced, enriched, has an enriched amount of quarks or an enriched number of gluons, okay? And so that's a well-defined quantity. And that's a well-defined quantity that you can compute in perturbative QCD. And it's also related to the seminar we had last Monday, where there was these topics and they were mixing. In principle, you can unfold things and try to go back to some version of the definition of quarks and gluons based on essentially two measurements. Typically, I don't know, if you make measurements of, I can't remember exactly which one or which is which. If you make di jets, you're probably going to have more gluons. If you make Z plus jets or W plus jets, you're probably going to have more quarks. And again, that means measure the two. It's not 100% quark. It's not a well-defined quantity of quarks and gluons. But in a certain model, at a certain order, you can try to measure the two. And one is going to be enriched in quark. The other one is going to be enriched in gluons. A typical use case, the reason is, what do you care, again? Many of the BSM models tend to produce more quarks, while in that case QCD would tend to produce more gluons. So if you find a way to enhance quarks versus gluons, you tend to enhance your BSM signal versus QCD background. Another use case is typically if you want to make vector boson fusions or Higgs to so I don't know, Higgs produced in vector boson fusion. That's typically two forward jets and some Higgs in the middle. The typical background you would have will have gluon jets in this case. And so if you want to separate the Higgs in VBF versus QCD background, enhancing the quark versus suppressing the gluon is something you might want to do. And actually this is something that is sort of already done in, so the experimental cuts do already have some cuts which go in that direction. So I'm going to use, the first technique I'm going to study here is, well, trying to say that the only thing you need to guess about quark versus gluon is that one radiates more than quarks. Gluons tends to, they carry twice the current charge of the gluon, give or take. And so you expect more radiation in gluon jets than in quark jets. So what you're going to measure in this case, remember last week we had one of these guys which was exactly designed for this, which was the angularities. So I'm going to define lambda, let me put a parameter beta, which is the sum of all the particles inside your jet at Zi times theta I to some power beta. And again, in principle, it's theta over R. Okay? Alternatively, you can define C1 or E1, that doesn't matter, which is the sum over I and j. And so theta I here is the angle between the jet axis and particle I. You can define things theta with I and j belonging to the jet of Zi, Zj, theta ij or r, the parameter beta, and in a way, to some extent, it doesn't matter for what I'm going to say. So does this work? So obviously what you're doing here is you're really measuring, you're measuring radiation away from the jet axis, okay? So this is generally something that you'd expect would be smaller for quarks than for gluons. And so if you say I'm putting a cut on this variable, I'm only retaining values smaller than something, you'll definitely enhance your quarks versus the gluons. So there's a few, let me proceed with the expressions for this. I'll discuss the potential caveats that we've missed later. So the calculation for this works essentially the same way as for the mass. If you put beta equals 2, this is actually exactly the expression we had for the mass 2 weeks ago, all right? So this is, quote unquote, just a generalization of what you have for the mass. And so you know that you'd expect, and again, let me make sure I get the factors right and notations right, you'll have, so you want to put a cut on V, so you're going to say, I'm going to call quarks if lambda is smaller than some lambda cut. And the probability for lambda to be smaller than lambda cut, so your quark efficiency as a function of lambda cut is just going to be, well, this probability, and that probability is exactly sigma of lambda by definition. So this is going to be sigma. Did I switch on the mic? Yes, that's good. That would have been great. Sigma of lambda cut, which is the integration from 0 to r squared d theta squared over theta squared, the integration from 0 to 1 dz. Let me take the soft limit, dz over z of alpha s z theta pt over pi. I need a factor of c quarks, so cf in this case, times theta of z theta over r to some value beta bigger, sorry, I'm missing something, bigger than lambda cut. And so that's the exponential of this. Sorry, I'm missing the exponential, so let me drop the lambda here. There we go. Okay, so exactly the same calculation. And by definition, if you put a cut, you're retaining value smaller, which is the sigma. And the only difference with respect to what we did for the mass 2 weeks ago is that now there's an extra parameter beta here. So if you take, to see what the physics is, it's always helpful to assume fixed coupling. You can do the calculation with running coupling, any number of loops if you wish. That's just a technical difficulty. Except that you have functions and you don't know exactly what to do. So this is going to be the exponential of, at fixed coupling, I'm always going to stick to fixed coupling in order to highlight the physics, of minus, and there's a factor, 1 over beta plus 1? 1 over beta. Yeah, so it's minus alpha s cf over beta pi again, you'd expect 2 logs, right? One soft, one collinear. And so at the end of the day, this is what you get. Okay? What happens for gluon jets now? Because I have the quark jets, I need the gluon jets. If you put the gluon jet here instead of the quarks, not much changes. You replace CF by CA, and you replace CF by CA here. And this is interesting, because you see here that your gluon efficiency is just your quark efficiency to a power CA or CF. That's something that people call Casimir scaling. In another word, maybe one way to view this is that if you try to make a ROC curve, so trying to get the your quark versus gluon efficiency, you're going to get a curve like this, independently of the PT of the jet, independently of whichever beta you choose, independently of the jet radius. That holds at leading log, okay? So there will be some corrections. If you start making the hard collinear corrections, for example, your P of Z will have a B term, a hard collinear term, which is different from quarks, slightly different from quarks and gluons, which is very slightly different. Multiple emissions will change that in a very small way as well. Running coupling doesn't change. If you put the running coupling, you can still factor out the CF or CA, so that doesn't change. So you can actually do this calculation at next to leading log without too much trouble, as long as you stay out of the trouble of soft and large angles. But essentially, this is the leading log result, and that's what you'll get. All right? So is there anything? So this is what you have. There's two things which I need to discuss. The first one is, I told you, performance in terms of just looking at the ROC curve is not necessarily all there is, and it's not only the only thing I want to discuss. I also want to discuss, say, resilience, and by resilience I mean, in this context, this is a perturbative QCD calculation. I want to check whether this is going to be affected by all sorts of non-perturbative effects, all right? So the take-home message in this case is that the performance won't change if you change PT. Again, this scaling doesn't change if you change PT. Now, on the other hand, if you increase PT, you open up, say, if you increase PT for a given, look at this page, for example, what happens if you increase PT? Imagine this is 1 GeV. You're essentially going to move this boundary up or move this boundary down as you wish. You essentially open the phase space. If you double PT, you increase the phase space between the higher energy and lambda QCD, essentially. So the higher you go in PT, you expect non-perturbative corrections to go like lambda QCD or some non-perturbative scale divided by PTR to some power. That's a generic property of infrared and collinear safe observables, that non-perturbative corrections are power suppressed. And so this means that if you increase PT, your performance won't change much, but your resilience will increase because you stay away, you reduce your non-perturbative effects, all right? So this is one comment. The second comment is about both these expressions somehow. So the question is, what are the i's that contribute to this sum, and what are the ij's that contribute to this sum? In this case, so ij's can take two kinds of values. Let me call, if you have something like this, let me call the hard part in this kind of resummation is well defined, and these emissions 1, 2, put I in the middle and N at the end. Obviously, if you take I and J both different from 0, this is going to be double soft, and so that's suppressed, compared to having either I or J being 0 and the other one being 1 to N, okay? So the sum in here is going to have something which is I equals 0 and J runs from 1 to N, and that's what we want, because in this case it's just that you can factor out that 0 is 1, and then this is just a sum over the emissions, and all the machinery for resummation we developed works. In this case, the situation seems to be obvious, right? I equals 0, the angle with the jet axis is expected to be 0, and I equals 1 to N, the angle to the jet axis is essentially the angle of the emission, and so this holds as well. This is actually not quite right. And the easiest way to see this is if you look at a simple case with one emission, where imagine I have a hard emission here. I'm drawing this as a function of whichever axis goes through the two emissions. And so a soft emission here, so this is Z, this is 1 minus Z. and I'm having an angle theta between the two. The question is where the jet axis in this configuration. And the jet axis, in the usual sense of making the sum of four momenta of the particles in the small angle limit, is essentially going to be the say center of mass of these two guys. So the angle here will be 1 minus z theta, and the angle here will be z theta. Okay? So now if you try to compute this quantity for this guy, you'll get something which is lambda is z 1 minus z theta to the beta. That's the contribution from this guy. And the contribution from this guy is going to be 1 minus z times z theta to the beta. So in both cases, I'm taking the soft limit, so I can drop the factors 1 minus z. So this guy gives me a z theta to the beta, and this guy gives me a z to the beta, theta to the beta. All right? So as long as beta is bigger than 1, strictly bigger than 1, I can neglect this contribution, and I'm fine. So this is the contribution from the emission, and this is the contribution from the leading parton. And in this case, I only retain the contribution from the emissions, and if I have n emissions, I'm just going to sum these n contributions, and we can unfold the machinery. Now, if beta equals 1, these two become equivalent, and if beta is smaller than 1, this one becomes dominant. And this is an issue to generalize to n, well, this is a bigger issue if you try to generalize this to n emissions, because what's going to contribute is not the emissions themselves, is the recoil effect they have on the leading parton, all right? And so at leading log, for beta equals 1, this is just going to give you a factor of 2, which is subleading, so it's actually going to be next to leading log. But for beta smaller than 1, this recoil is leading log. And this is more complicated, because if you have n emissions, you need to work out the recoil in the 2-dimension of the jet. And this can be handled by Fourier transform or Mellin techniques. But still, it's a slightly more involved calculation than the one we did for the mass 2 weeks ago. So essentially, what I did here, strictly speaking, applies only to beta bigger than 1. Now there's a way to get out of it, which is find a way to define your jet axis so that your jet axis is here. And there are ways to do it. I don't want to enter into the details. Something called the winner-takes-all axis will do something like that. And at the end of the day, that means that if you want to use these objects with simple QCD calculations and beta smaller or equal to 1, you'll have to watch out how you define your axis. This is one of the reasons why people tend to actually prefer correlation functions over angularities, because this doesn't apply here. There's always the this doesn't have to make a reference to a jet axis. Okay. So this is actually a bit depressing. You expect, naively speaking, you say, I'm going to increase PT. If I increase PT, I have a huge phase space I can take advantage of. Possibilities become countless. There's many things I can do. The more emissions I have, the more constraints I can put. At the flux, you always get Casimir scaling, and that's it, all right? So people try to think about something different. Is there any very simple quantity you can think of? If I tell you gluons radiate more than quarks, gluons radiate more than quarks, what's the simplest quantity you can think of that's going to measure this? If you radiate more, you have more. What do you have more in your jet if you radiate more? More particles, multiplicity. And that's actually one of the very first things which had been done. And again, QCD people are going to tell you, or perturbative QCD people are going to tell you, what the hell, multiplicity is not a computable quantity. That's the textbook example of something which is not infrared and collinear safe, all right? And so multiplicity, fine, that's actually a very good quark-gluon discriminant, but it's something where all this can be just binned and, well, trashed. Binned, maybe more experimental concept. And so that doesn't work. I cannot apply this to multiplicity. And actually some people have managed to find a way to define a multiplicity which does work and which is calculable. And so this is the second thing I'd like to discuss, something called iterated Soft-Rock multiplicity. Question is, how do you define this? Do you remember how Soft-Rock works? You start with a jet, you cluster all the constituents of this jet with the Cambridge algorithm, which orders things in angle. And then you undo this last clustering until one of the clusterings satisfies z bigger than z cut theta over r to the beta. If it does satisfy this, you're done. If it doesn't satisfy this, you just drop the soft one and carry on with the hard one. Okay? So the idea here is to repeat this. So what you're going to do is, if you have a jet with any, let me draw this here because I'll need to save space. If you, again, a jet with this sort of things, order in angle, all the emissions here, essentially all the subsequent emissions are essentially concentrated in these guys, at least at leading log. What you're going to do is essentially undo the clustering, and instead of stopping when you find something, you carry on. So what happens, imagine this one is soft enough, is too soft, you drop it. Imagine this one is hard enough, you keep it. This one being hard enough, you keep it. This one soft, you drop it. This one hard, you keep it, say. And what you're going to do is essentially count the number of times you've had a declustering which passes this this condition. All right? So again, I can draw this. This essentially defines a line. All right? Z equals Z cut theta to the beta defines a line. For beta equals 0, it's just a Z cut. That's line of equal energy. For beta bigger than 1, it's actually going to tilt this line here. And for beta smaller than 1, it's actually going to be a cut like this. So what you're going to say is, I'm going to decluster my jet step by step, and every time I have an emission which is somewhere above this line, I'm going to count it. Leading log, that's actually a beautiful calculation, because at leading log, all these emissions are independent. The probability for a given emission to be inside this region is evident. This is just, let me call this A, which is the integration d theta squared over theta squared dz over z alpha s over cr over pi times theta of z bigger than z cut theta over r to the beta. That's just essentially the area of this guy. And so if the emissions are independent, the probability to have n emissions is just a to the n divided by n factorial times e to the minus 8. It's just a simple Poisson distribution. The same way that multiplicity would typically be is expected, at least for independent emissions, to be a Poisson distribution. And this means that if essentially A is proportional to the color factor, if you increase the PT, you increase the area. And as you increase the area, you increase the differences between the two Poisson distributions. So the advantage of this is that you can essentially just by increasing the size of your area here, you can enhance the degree of the discriminating power between quarks and gluons. So remark number 1, you have to, that would be beta equals 0, that would be beta positive, and that would be beta negative. If beta is 0 or positive, this is not that well defined, right? This becomes infinite, which means it's actually at some point going to be regulated by whatever non-perturbative physics you have. So the typical use case for this is negative beta, or I don't know, positive beta works, but then you have to put another cut if you want things to stay perturbative. So this is going to be negative beta, and there's a specific value of beta which is appealing, especially in view of this. You're going to say, remember, I want to make a perturbative QC, a well-defined, in the perturbative QCD sense, definition of multiplicity. That means I want to stay away from harmonization. all right? So the typical best case you're going to do is make a cut which is essentially coming as close as possible to here. So you maximize the area by keeping away from this. So it's typically a KT cut that you would do. And KT cut is essentially a cut in Z theta. So that would be beta equals -1. All right? And again, there's a trade-off, the usual trade-off between performance and resilience against non-perturbative effects. If you lower your cut, so essentially Z cut is, this is the value, this value here is Z cut. If you lower the value of Z cut, so remove this cut down, if you decrease the value of Z cut, your area increases, so your discriminating power, your performance increases, but you're going close to your hadronization, so you're becoming more and more sensitive to hadronization. So there's again this trade-off between being sensitive to hadronization and being efficient. And so this essentially has the opposite behavior as what we saw here. Namely, if you keep, say, a cut, let's say, if you keep a cut which would correspond to, say, a few GeVs to stay away from non-perturbative physics, somewhere like 2, 5, 10 GeV, 1 is asking for trouble. If you increase PT, you increase the area, and so you gain some discriminating power, but your resilience essentially is kept fixed. Okay? So in this context, increasing PT doesn't change the efficiency, but increases the resilience, your resilience against non-perturbative effects. In this case, increasing PT increases your efficiency, but doesn't change your resilience. That's something you can test via Monte Carlo, for example. It's actually fairly obvious. Is there anything I want to say in this context? Is there any question? So I think these are really the two stereotypical examples of quark-gluon discriminator. One is generally a shape, and shape tends to exhibit some scaling like this. Iterated Soft-Rock multiplicity is generally a multiplicity measurement, and multiplicity, so shapes tend to have a Sudakov behavior, multiplicity tends to have a Poisson behavior. In terms of discriminating power, shapes tend to lose against iterative, against multiplicities. Now, again, the drawback is that this is a textbook QCD calculation. If you know what you're doing, you can actually bring this to next leading log without too much trouble, as long as you stay away from non-global logs and soft large angles. There are ways to do that. I can comment on this later. Or keep the jet radius small enough. So this is something where the QCD calculations can be brought way beyond this accuracy. In this context, at some point you'll start getting in trouble. A leading log is fine, next leading log, good luck with it. There will be some nasty effect at next leading log, especially some related to clustering effects. At some point, at next leading log, you'll start having cases where two emissions are at similar angles. And an emission like this can be clustered with that, an emission like this can be clustered with that, and this is something where that's asking for trouble. That's the same level of difficulty as non-global logs there. So in terms of, again, of just QCD, this is easier, this is handled much more easily than this, all right? So let me check, did I forget anything? So essentially, yeah. That's, I think, what QCD tells you, that you can understand. So the main message here is that based on QCD, we did some QCD calculations, and QCD essentially guesses about power corrections. You understand why, depending on where in phase space you look, depending on what cuts you put, you understand how this object compares with this, all right? So I think the next step I want to do, it might actually be a slightly longer one, is discussing groomers and prong finders. For once, I've actually been ahead of schedule. That's great. Everything happens. So maybe now is a good time to have a 10-ish minutes break, if that's fine with you, Marco. And then we'll go back with with groomers and prong finders. Okay, one quick point I forgot to mention, welcome back, is, okay, might be obvious to all of you, but just in case to make it clear, if you have two Poisson distribution of a certain parameter, A was the parameter of the Poisson distribution in the previous calculation, both the average and dispersion of the Poisson distribution is proportional to A, and so this means that if you increase A, you increase the separation, all right, because they get further away. So, what I want to do now is discuss, it's an application which falls more in the category of separating W bosons versus W Higgs or Z bosons, say massive bosons versus QCD background. Typically, if you want to measure a massive object, the natural thing you're going to do is measure a mass spectrum. And you'd expect a mass spectrum to show a peak in your signal and to show some background distribution. So the question is, can you essentially use QCD to understand what that background distribution would be for the common tools you'd be using in that context? And the common tools you'd be using in that context are essentially what you take as either groomers, which are essentially meant to reduce the sensitivity to non-perturbative radiations, or clean your jet and keep only the hard stuff in it, or N-prong finders. And I'm actually going to take two cases here. I'm going to take the case of the modified mass drop tagger, or soft drop. I can essentially kill two birds with one stone here, and the case of trimming. So give or take, that's CMS, that's Atlas. So there's, for this, I'll need to compare the mass distribution, the plain jet, I'll refer to as the plain jet, which means the jet where you don't do anything, your jet out of the box, versus what you get in these two contexts. And so I added here on this blackboard what you have, that's the equivalent of what we discussed of the pocket formula for the case of the jet mass. The jet mass V is Z theta squared. So you build a dimensionless ratio m squared over PD squared r squared, and so you have to impose, that's rho, you have to impose that Z theta squared is bigger than rho, and that gives you essentially a double log in 1 over rho at leading log and fixed coupling. There'll be corrections, but this is all I need at the moment. So in terms of the Lund plane, Z theta squared is a line like this, and so what you do is you put a cut here where you veto emissions up there. And one thing I need to discuss, at which point do you become non-perturbative? All right? So imagine I'm putting a non-perturbative scale here, say mu non-perturbative. This point where you hit the hadronization region is essentially the point where Z theta times PT, that will be the KT of your emission, when the KT of your emission is your non-perturbative scale, order a few GeVs, okay? And you see that the point where it is actually the closest to the non-perturbative region is the point at large angle. So that's the point where theta equals R and theta equals R. Okay, so that's essentially where you get this. And so from this, you get trivially that, did I get this right? Yeah, you get trivially that rho, let me make sure I get, did I write it down in terms of the mass? Yeah, I wrote it down in terms of the mass. That the mass at which, the squared mass at which you'll get non-perturbative, it's just replacing this expression and these guys in it, that's absolutely trivial, and you get mu non-perturbative times PT R. So this essentially, if you look at a mass spectrum, as a function of rho or the mass, essentially you'll get rho equals 1 in this context, which is the, if you plot this distribution, that's the cumulative distribution. Take the derivative to get the mass spectrum. The derivative is going to bring a factor alpha SCF over pi log 1 over rho times the exponential. So you'll essentially get a distribution which does something like this. That's exaggerated. Yeah, I'm very bad at drawing curves on the blackboard. Yeah, that's a bit better. So that's what people usually refer to as a Sudakov peak. You get a rise here because of, say, the dominant behavior is going to be alpha S log. And then if you go down, in this case, you get the suppression due to the Sudakov factor. So there's a peak, and essentially at some point here, you'll hit a region where in this region, you say this is going to become dominated by non-perturbative physics, and this is this scale, all right? Now, with this, what happens in these two cases here? That's what we're trying to address now. So let me start with the case of the modified mass drop in soft-rock, and again go back to this picture where this is, say, your leading parton, and you get a bunch of emissions out of it. So emission 1, 2, I, and N. And again, modified mass drop proceeds by declustering a Cambridge kind of clustering tree. So if you have a system like this, what's going to happen, think about the way the Cambridge algorithm work, it's essentially going to start from small angular distance to large angular distance. So what's going to happen is you're going to recombine these two, then these two with this guy, then these two with this guy and this guy. So essentially when you do the clustering, you go from small angles to large angles. So when you decluster that history, you go from large angles to small angles. So the way I drew this here is essentially that theta 1 is much bigger than theta 2. So I'm assuming my angles are ordered in this case. Now, at least at leading log, every of these angles here, let me call this theta I. The emission here is going to be Zi. QCD tends to be angular ordered, which means that any subsequent emissions from any of these emissions of the leading parton are going to stay essentially within. So if you look at extra emissions from this guy, this is going to stay within an angle of order theta 2. So at least at leading log, since my angles are strongly ordered, all the subsequent angles of the emissions within this say branch are going to be at angles much smaller than theta 2, so just going to be clustered with this gluon before they get clustered with the main parton. So at least in this context, I don't need to worry about any of the internal dynamics of this guy over here. There's one small side note to this, which is if you make a soft emission out of this guy here, if you make a soft emission, you get a log from the soft. So there are cases where you get logs when the angle is of the order of theta 2, and in this case, clustering can do all sorts of nasty stuff. But if the emission is soft, you essentially don't really care, at least for the mass, because you have a soft emission from here. If this emission is kept, then it's a small correction to the mass of your jet. So secondary emissions in this context can be neglected. So this means I can really view this as if it was QED, sorry, and I can really view this declustering procedure as going progressively, iteratively down this series of emissions. All right. So what's going to happen is you're going to start with the first one. You probe the first one, and remember this is going to stop when the condition Z bigger than Z cut theta over R to the beta is satisfied. So I'm going to probe the first emission. If it satisfies this condition, I'm fine. This is my whole jet. All right. If it doesn't, I'm going to discard it, carry on with the next one, and again probe it. So what's going to happen is I'm going to peel off all these successive emissions until one of them is above the cut. Okay. So if you wish, if I can draw this again, graphically speaking, what you do have is your kinematic limit, your line of a given beta. Let me take a positive beta for a change. What happens is that if you have a bunch of emissions ordered in angle, let me try to do something a bit more. Yeah, a bunch of emissions ordered in angle. Something like this, say. Let me add one here. So what's going to happen is you're going to first test this large angle one, you're going to remove it, test this large angle one, going to remove it, test this one, and stop. Okay, so at the end of the day, your jet will keep all the emissions to the right of this one. Okay? What's the mass of this jet? Assuming all the emissions are sufficiently far away. The mass of the jet is essentially just going to be the mass, so the mass of the jet, so let me call the rho, is going to be the sum of Zi theta I squared, again, theta I over R squared. That's the mass, the dimensionless mass of this jet. And the question is, so in here, I'm going to, the sum which is here runs over all the emissions in this region, right? So it's the sum really in the emissions in the region where you're at the same time above the soft drop line and on the right of the first emission that passes the soft drop condition. Now, there can be two cases. The first case is when this emission is at the same time the one that dominates this sum. In this case, the mass is given by this emission. The other case is you might, as I draw it here, this emission there actually has a contribution to the mass which is larger. But fine, by definition, it's at a smaller angle, and so in this case, what I mean to say here is that if this is the mass, what do I need to veto? The question is, what do you need to veto? What's the status of the cancellation between real and virtual? That's what you need to worry about at leading log. All the emissions which are outside, what's their fate? All the emissions which are outside, they don't contribute to the mass by definitions. I've removed them from the jet. So all the emissions outside this region, they will cancel between real and virtual. The emissions which are at angles, well, the emissions which are in this region down here also don't contribute to the mass by definitions, because I found an emission which was larger here. So if this emission dominates the mass, what you need to do is veto all the emissions which are up here, which would give you a larger mass. If you do have an emission here which is not the same, so imagine you have this two-case situation where the mass is here, you need to again veto the emissions which are here. The nice thing about this is that this angular cut doesn't play any role here, because the emission that at least dominates the mass is always going to be at a mass which is larger than whatever is relevant for this angular cut. Okay? So at the end of the day, what you need to do is veto all emissions which are at the same time above the soft drop line and would have given you a larger mass. So in this case, your sigma of rho is going to be the exponential. I think I kept forgetting the exponentials in my notes. 0 to r squared, that's actually a big difference. D theta squared over theta squared. The integration from 0 to 1 dz p of z. Alpha s over 2 pi. Put the argument there if you want. So you need to veto emissions which are here. So this means in the whole phase space except this hatched region here, you get a cancellation between real and virtual, and here you only keep virtuals. So essentially what happens is that you keep a Sudakov factor with this radiator. And the Sudakov is z theta over r squared bigger than rho, theta of z bigger than z cut, theta over r to the beta. So this per se is actually quite an amazing result, because so this result was essentially derived something like around 2013, something like 1 or 2 years before that. People were just saying, getting any hint at jet substructure with these techniques, you essentially just doing all sorts of crazy stuff on your jet, and so forget about trying to compute this in QCD. So this actually not only shows that it's possible to compute things in QCD. That was actually the first serious jet substructure calculation done for the mass drop tagger. Soft drop was done a year or two later. Not only it shows that it's doable, it also shows that the structure is damn simple. This is just an exponentiation of a Sudakov the same way it was without any fancy substructure technique. So just the fact that this exponential holds is also something, something beautiful. Now, that's what we have at hand. Again, if you take fixed coupling, you'd expect double logs, right? Because this is an area, so integrated above this will be dominated by soft and collinear emissions. And if you do this calculation, you'd actually find there's a so the mass here has a transition point, right? This is Z cut times R in terms of KT. So if your mass is in this region here, this cut has absolutely no effect. So if you look at the result at fixed coupling, you'll get something which is exponential of, let me do it this way, exponential of minus alpha s CR over pi 2 pi log squared 1 over rho for rho bigger than Z cut. That's essentially your region where your KT is your rho is big enough so that whatever you do, this theta constraint is actually never active. And on the other hand, you're going to get exponential of minus alpha s CR is minus here over 2 pi times it's log squared 1 over rho minus, and out of my head, I think it's a 2 over 2 plus beta log squared Z cut over rho. And again, I told you can essentially read it off the graph. I'm essentially writing down this whole object as this triangle minus this small triangle down there. It's that simple. And so that's for rho smaller. I'm missing a closing bracket here. That's for rho smaller than Z cut. Okay, anything interesting in that context? First, if you take the limit beta going to infinity, all right? If beta goes to infinity, this goes to 0, so this cut is never really there. Typically, if you take beta going to infinity, you take this line and you move it progressively to the left, meaning that at some point it doesn't change with respect to the initial jet. And indeed, beta going to infinity, this term drops, and you go back to the plane jet mass case. Okay? A specifically interesting case is the case beta equals 0. Because if you take beta equals 0 in this case, this factor just becomes 1. And so for beta equals 0, and again, let me take rho smaller than Z cut, what you'll get is just the exponential of minus alpha s CR over 2 pi, and this thing here becomes 2 log 1 over Z cut log 1 over rho minus log squared 1 over Z cut. This is not very clearly written. So the idea is if you take a coefficient 1 here, the log square here cancels again the log square of rho in this term here. And so this is actually interesting. It means that the behavior for the modified mass drop mass distribution is no longer a double log, it becomes a single log. In terms of the series expansion, the perturbative series expansion, this actually means that you can, it means essentially you get higher accuracy for free, give or take. So this is actually a nice thing in terms of the QCD properties of this guy. This is actually a nice thing. And this may be related to the reason why modified mass drop or soft drop beta equals 0 is probably the most commonly used tool in the jet substructure world. Any questions so far? Let me make sure I didn't forget anything myself. Okay, I think this is okay. So there's a bunch of things I like to do with this. Let me erase this so I can do partially things here. The first thing I want to do is have an idea of what it gives in terms of the mass distribution. So if you go back to the mass distribution, so this kind of mass distribution, you see that as long as rho is bigger than z cut, the distribution for mass drop or soft drop is the same as the plane jet mass distribution. So this means that until you hit a region here which is z cut, sorry, I wrote this one a bit small. Until you reach z cut, this distribution is exactly going to be the same. Then let me put z cut a little bit more to the right so I can show this a bit more easily. Then once you hit it, essentially what happens is that your radiator is reduced because you don't veto this. So if your radiator is reduced, the derivative is going to be reduced as well. So as long as you're here, this is going to give you something which goes like this. And as you lower beta, you're going to get something which becomes flatter and flatter. So that would be plane. Say beta positive until you hit beta equals 0. I could have drawn this in color. So one thing is that as long as so imagine you're doing this as a way to measure signal versus background. Imagine you use this as a way to get your distribution of the QCD background distribution against W's. As long as your the mass region you're interested in is in this area, you're actually going to reduce the background. So one thing is that you're more or less forced into something like that. One thing I won't discuss, it's in the lecture note in the book, if you're interested in, is the effect on the signal. So if you try to measure the W distribution, essentially I told you 2 weeks ago that the mass peak, the W peak, instead of looking like a nice peak, is actually going to be an ugly, smeared and shifted bump. These technique actually, by removing the underlying event and pileup region, essentially cutting out this region of underlying event and pileup, this is going to bring back this W mass peak close to something reasonable. So I think if you generally want to discuss the discriminating power between W's and QCD jets, or two hard prongs and QCD jets, you probably need to discuss both signal and background. But I won't go into this at least right now. So you also can compute the signal efficiency for W. This is all done in the book. So if you're interested, either ask me specifically or go there. I don't want to get carry too far away of this thing. So this is one thing. Essentially, your distribution, you get a reduction in this region, and now you can argue that this is actually the region of interest. Now, the other thing I'd like to discuss, and that's probably going to keep me busy for a bit of time, is when do you start hitting the non-perturbative region? Okay, this whole question about, so there's a whole question. Initially, what you want is find prongs, and so that's essentially related to the question of the W. Indeed, you want to find something which has a hard prong in it, and by hard you mean above this cutting line. So really the question about, to discuss more this question about the prong finder aspects of this, I think you generally need to go into discussion of both signal and background, and that's not necessarily what I want to go into, at least not this week. I may touch on this next week. What I want to discuss more is this question about grooming, the grooming aspects. And the grooming aspects is really, as I just said, trying to get away from the soft contamination, the contaminations from radiation at soft and large angles. And so obviously this does the trick, right? We know that the underlying event lives in this region of the phase space, and you're explicitly cutting it out. So in terms of doing the grooming job, this does a nice job. One aspect I'm trying to discuss in a bit more detail is the hadronization aspect. And you can do this in two different ways. The first one is go back to this scale here and check what it gives. So the question is, if I start to measure this distribution here, at which point do I stop trusting it? At which point do I stop believing there's a QCD explanation, a perturbative QCD calculation for it? So I told you what you want is essentially you want, let me reuse this graph here. What you want is to stay above some non-perturbative scale. I don't want to go below this. The question is, when do you hit this? You're actually going to hit this when your mass touches this point. That's the point at which, obviously, your mass distribution is going to be sensitive to the physics of what happens below this non-perturbative limit. And so this point is the point where z theta is equals to your z theta pt is equals to your non-perturbative scale. That's the kt, which is equal to non-perturbative kt, and the point at which your mass and soft-drop line intersect. And so at this point, you're on the soft-drop line. So on this point, essentially the intersection of this line and that line. And so this tells me that z is equals to z cut times theta over r to the beta. And again, this is fairly simple math. Let me give you the answer. This is a calculation I've probably done at least 50 times by now. If you do this, well, I know, that's trivial, right? That's the two equations. You extract z and theta from this system of two equations. And once you have z and theta, you can find the mass, which is z theta squared times pt squared. And you find that your, do I have it here? Yeah, mass non-perturbative squared is mu non-perturbative ptr times mu non-perturbative over z cut ptr to the 1 over 1 plus beta. This is elementary school math. At least that's what I would have hoped until my own kids went to elementary school. So first, limit beta, whenever you have an expression like this, it's always nice. You easily make mistakes. Check the limits, all right? Beta going to infinity is a trivial one. If beta goes to infinity, you expect to recover whatever I had above here, okay? And so this is great, because beta going to infinity, you do get recover that result. Now, the other thing is that as long as mu square ptr, essentially the kt of this scale here, mu non-perturbative is way smaller than z cut ptr, so this is something which is smaller than 1, actually much smaller than 1. In practice, it might not be that small. But so this is for any reason, well, this assumes that beta is positive, because if beta is negative, you actually put a cut in this direction and you start hitting the non-perturbative region on the opposite side. So this assumes positive beta. Not strictly positive, positive or 0, sorry. So at the end of the day, this means that this non-perturbative scales is smaller than the one you had for the plane jet mass. So if you look at this distribution here, if you're saying the plane jet mass hits the non-perturbative region here, so I can trust it above this point, for the soft drop mass, this point is going to be shifted down, and for the mass drop mass, the point is going to be even further shifted down. So this means essentially that the region over which you can do genuine perturbative QCD is actually enlarged compared to the region where you would do genuine perturbative QCD for the standard plane jet mass. There's actually another way to view this. I'll discuss consequences on this. That's one of the points I want to make. The other observable you can look into is even if the mass, imagine the mass is somewhere in the bulk of this distribution. So let me take a mass somewhere there, all right? By the way, just a side note before I get there, you see here this kind of power behavior of non-perturbative effect. You'd expect something that scales like powers of ratios of relevant KT scales. Now, so what you may want to do is imagine I have a mass, a jet which has a mass somewhere in here. It's still going to be affected by non-perturbative effects. And you expect this non-perturbative effect to scale again, like powers of the proper KT scales in the problem. the same way we discussed last week the effect of final state, initial state radiation, hadronization, underlying event on the PT of the jet. You can make the same sort of calculation for the mass of the jet. And so again, let me make sure I get this here. I get the same notation here, so at least it's coherent between the different objects. So you can say if I have a jet of a given mass, how are non-perturbative effects expected to shift this mass? And we can actually show that for the plane mass, delta m squared for the plane mass is essentially going to be proportional to the color factor of your jet times some non-perturbative scale times PT times R. Okay? Oh, okay, that's what you get. Essentially using the same technique as the ones I told you last week that would for the PT give you a CR lambda PT over R, or CR lambda over R, sorry, minus CR lambda over R. This is the scaling you get. Essentially the mass is a weight, it puts more weight. Because of theta squared, the mass puts an extra theta squared factor close to the edge, so you get an extra R squared factor. That's no, R scaling is expected once you know the PT scaling. Okay, so far so good. The question is what happens if you now do this with a soft-drop mass. So I go back to my case where I have a mass somewhere, say, yeah, let me take a mass somewhere up here, okay? Sorry. I'm taking a mass somewhere up here. Well, how do you expect this mass to be shifted? And actually you can make a very hand-waving arguments to guess the scaling of this guy. Because you know that if you have the mass up here, the angle you're going to be sensitive to is at most this angle here, right? Whatever happens, the soft-drop procedure is going to stop at an angle which is smaller than this. So effectively what you're doing is actually replacing being sensitive to all angles below the jet radius to being sensitive to all angles below this dashed line. So what happens is you're actually going to get a scaling which still scales like CR lambda PT, but with an effective radius which is given by this. And again, this is a calculation I've probably done as many times as this one, where if you take this guy, this angle here satisfies Z theta squared over R squared equals rho, and it satisfies at the same time Z equals Z cut theta over R to the beta. And if you do this, again, let me just copy paste what I have here. What you find is, do I have delta m here? Yeah, I do. You get that your effective radius is R times m squared. Let me put that there so I can discuss it over here. Yeah, that your effective radius to have it squared is R times rho, that's rho over Z cut to some power 1 over 2 plus beta. So there's several points I want to make. This is actually, this has several important consequences. So the first nice thing about this kind of computation is that, well, the first thing is that it pushes your non-perturbative boundary to lower values. Namely, you have a larger phase space where you hope to be able to do perturbative QCD. The second thing is that even if you go in the region where you would trust your QCD calculation, there's still some expected non-perturbative correction in that region. And so the fact that you do modify mass drop or soft drop is actually going to reduce your non-perturbative corrections by a factor of rho over Z cut, which is smaller than 1. So again, this is smaller than 1, so this whole guy to the 1 over 2 plus beta, this is, at least in the resonation region, much smaller than 1. So it means that not only there's a larger phase space over which you can do perturbative QCD, but on top of that, in that region where you trust your perturbative QCD calculation, your non-perturbative corrections are reduced. So actually, it's a win-win situation in this case. It also has consequences in terms of how you do perturbation QCD. essentially what happens, remember all the nasty stuff in there. This guy, which was actually not very user-friendly, doable, but process-dependent. You need to compute it process by process. It's a complicated set of functions, complicated set of dipoles, way more hard calculation than the back of an envelope thing we did here. Now, again, this guy here is the soft and large angle scales like the jet radius. These calculations actually did finite in angles, it's soft and finite angles, so that these contributions scale like the are powers of the jet radius. Now, essentially, these powers of the jet radius is going to be replaced by the powers of the effective jet radius. And if it's the effective jet radius, you know that instead of them being log, it becomes power suppressed. So in perturbative calculations, in all order perturbative calculations, doing this kind of things actually kills this contribution. Meaning that perturbative calculations, which initially, I remind you, were deemed to be complicated because you make crazy stuff for your jet. At the end of the day, they turn out to be simpler. There's a similar kind of thing for non-global logs, because non-global logs essentially happen, if you remember, when you have two emissions which are somewhere close to the boundary of your jet, at the edge of your jet. Now, if you do have an emission which is outside your jet somewhere here, and have another emission which needs to be inside your jet, so somewhere at least smaller, at angles small enough to be kept, this is again going to be suppressed by powers of your effective radius. So the bottom line is that soft and large angles and non-global terms, all the complicated business in your resummation calculations become much simplified. And essentially the basic rule of thumb is that these modified mass drop and soft drop calculations can be done using collinear physics. Okay? So this is genuinely the, this is generally a great property. The fact that not only non-perturbative corrections are pushed back, their size is reduced, and the description of the physics is actually not too complicated in terms of order. So the idea is then, well, if this is simple, can you measure this at the LHC? Can you compute it? Can you compute it in your office? And can you compare the two? That's part of what you were asking earlier, right? And so this has been done. And so I'll open the parenthesis here, which is what kind of tools do you need? Imagine now I want to make a perturbative QCD prediction for this mass. So obviously, you try to make your resummation calculation as precise as possible. And so essentially, the calculation we did a couple of years ago was next to leading log. There's actually a next to leading log calculation that exists in Sket. You can probably use it in, say, normal QCD as well. But essentially, this is known to next leading log at the moment. There's probably a way to make it NQ leading log as well if you really push it hard. The idea is that, so imagine this is rho. I want a distribution which does something like this. And that's, again, no fully drawn plot. I want a distribution which does something like this. That's better. So first of all, there's a region here which is non-perturbative. There's a region somewhere here which is non-perturbative. And that's a no-go for perturbative calculations. Then I would say there's a region here where rho is indeed small, and in this context, you'd expect the resummation calculation to give you the right answer. Now, there's a region here where the mass is actually large. So rho of order 1, rho finite, rho not much smaller than 1, where you'd expect the logs to be not too big. And in this case, your beloved fixed order calculation should do the trick. So this is typically the resummation calculation. This is typically the fixed order part. So in practice, what you can do is compute everything. You can compute, say, sigma or the distribution at your n to the whatever leading log, say sigma resum, at your whatever n leading law calculation. So currently k equals 1 or 2 are the standard choices. You can compute, and this is an analytic calculation, you can compute your fixed order calculation. Take any fixed order Monte Carlo. I guess if you were doing something like W plus J, black hat could do it. Bear in mind, yeah, and so just for the sake of the amplitude people in the audience, let me just say a few words about this. So the question is, what order of the perturbation theory does this start? So imagine I make dijets, okay? That's the standard place you would measure this, or W plus jet. You can extrapolate this to W plus jet if you wish. So dijet, you'd have colliding partons going into two jets. In this case, the mass is 0, so you essentially need an extra parton to get a non-zero mass. So this calculation starts essentially with a 2 to 3 process. That would be the leading order. And then if you want to go to NLO, you'll get a 2 to 4, and that would be Born level. You'll get a 2 to 4 Born level and a 2 to 3 with one loop. And that would be your NLO calculation. Dijets would give you this for typically for using NLO jet or MCFM, I believe. Well, no, probably NLO jet. I'm not sure. PowerHack probably does it as well. If you do W plus jet, I guess Black Hat can do this. MCFM can do it. Probably PowerHack can do it as well. So anyway, that's give or take the state of the art. If you want to go to next leading order, you start getting in trouble with the 2 to 3 calculation at 2 loop, which we would need for the vertical corrections, and that's when you chime in at some point, hopefully. So that's the state of the art. So now you get this, which is essentially leading order or NLO. That's the state of the art. And fine. Then one thing you can do is for the resummation calculation, I can expand the resummation calculation. This is an analytic expression. Expanded is going to be 1 minus correction of alpha s minus alpha s squared. And once you have this, what you want to do is make a unique prediction which combines these two. A unique prediction that's valid all over the phase space. And there's different ways to do that. One is just to say that the resum plus fixed order is the resum times the fixed order divided by the resum fixed order. Give or take, if you go in this region here, the resummation is essentially, the fixed order is valid, so these two guys will essentially be the same and they cancel. So in this region you recover the fixed order. If you go in this region here, actually it's the opposite. In this region, the fixed order expansion should be well captured by your resummation formula, so these two will cancel and you recover the resummation formula. There's a different one. This is called R matching, or it's a multiplicative matching formula. There's also expressions which use logs of sigma instead of sigma to do the matching, but that's one. So the idea, if you want to make a QCD prediction for this, you compute this as the highest precision, this at the highest precision, and you find a way to match the two together to get your prediction. So this has been measured by both CMS. So CMS measured it for beta equals 0. Atlas measured it for beta 0 to 4, as far as I remember. And at the end of the day, you can make a prediction. You can supplement your prediction with either analytic or Monte Carlo estimate of the non-perturbative corrections, which are expected to be small. And at the end of the day, you compare theory against data, and that tends to work beautifully. You see all the features you expect to see. I'll try to show you a few plots like this next week. I didn't want to show too many plots at the same time. So actually it works so well that one of the questions, so it's definitely a playground for precision physics at the LHC. Because one, mostly because you're actually pushing the perturbative region far away, and your resummation calculation can actually be done in a meaningful way, in a more easy way than trying to push the plane jet mass calculation in precision. So actually one of the prospects is trying to see if by measuring this distribution, you can actually extract the strong coupling constant, alpha s. So measuring this is this distribution, mass or another observable, but measuring groomed modified mass drop distribution at the LHC or soft dropped distribution at the LHC is one of the candidates to estimate alpha s. And this is, I think, this should be viewed as a, I would say, community effort, because it requires huge precision in terms of measuring things. You want to generally be able to experimentally make a precision measurement, which brings all sorts of technical challenging problems. The resummation needs to be pushed the same way when you do a fit of alpha S using thrust at LEP. You want n cube leading log, you want as many logs as you want. So you need to be able to understand this. You need to be able to understand properly the non-perturbative part, and you need to be able to go as precisely as possible in the fixed order region. So if you really want to make, say, particle data group level measurement of alpha S, this is something that that requires all sorts of inputs. All right. So over a few minutes I have left, I'm going to discuss the second case, which is trimming. And instead of doing the full calculation, I'm just going to assume I have one emission. Okay? And the question is, what's the trimmed mass in this case? So just as a reminder, trimming works by saying I'm going to take my jet, cluster it into small jets of size R, R sub, or R trim. I take a small jet radius R, smaller, trim radius smaller, or R sub. I don't know, R trim is a bit of a verbose kind of name. And among all these subjets that I find with this smaller radius, I'm going to keep all the subjects which carry at least some fraction of the jet energy. So I keep them if the PT sub is larger than some fraction F trim of the original PT jet. So far, so good. So if you have a situation like this, there's generally two options. Either theta is smaller than the jet than R trim. If theta is smaller than R trim, these two guys are in the same jet, and so they will be kept. There's only one subjet which carries 100% of the jet PT, and so the mass is Z theta squared PT squared. All things which look either like a Z or a 2 in the exponents are 2. That's sorry, I tend to write 2s like Z, so unless you know what you're doing, I understand it can be confusing. Now, if theta is bigger than R trim, then it depends. If Z is bigger than F trim, so if theta is bigger than R trim, this is going to be clustered into two different subjects. And so I'm only going to keep this one if the momentum fraction is large enough. So if Z is bigger than R trim, you get the same M squared and if Z is smaller than R trim, you get M squared equals 0. Okay? So what this means is that essentially all emissions which are at angles larger than the trimming radius and which have a momentum fraction smaller than F trim are not going to contribute to the mass. They're going to end up into subjects which are too soft to pass the trimming condition. In other words, the only contributions the mass will have are cases where either the mass is bigger, either the radius is smaller than the trimming radius, in which case they end up in the subject of the hard parton, or there are angles larger than the trimming radius, which means they end up in their own subjects, but they have a PT large enough above F trim. So if you look at this case, you'll get an expressions like the integration from 0 to R squared d theta squared with theta squared, the integration from 0 to 1 dz p of z, alpha s over 2 pi, theta of, so imagine I make the cumulative distribution, so I want z theta squared over R squared bigger than rho. That would be your standard constraint on the mass. But you'll get also a theta of either theta smaller than r trim, or, and let me, again, I'm taking some freedom to write text in theta functions, or z bigger than f trim. That's essentially the kind of thing you'll get from one emissions. The thing I don't want to show, but that can be shown actually, well, you can probably get convinced even without doing any calculation. Again, if you have any number of emissions which are soft and collinear and independent, you'd expect this constraint to apply individually on each emission. And so at the end of the day, your recent calculation sigma of rho is just going to be the exponential of minus this. So this is the kind of thing that's going to happen. Now, graphically, let me start afresh. Good, more or less on time. This means that, so the question is, what's this region here? This region, well, the region in this constraint. That means that I'm going to keep emissions which are above a certain z, f trim. And so if you forget about this constraint, this z bigger than z trim, that's exactly the same constraint as z bigger than z cut that you would have for modifying mass drop diagrams. Beta equals 0 soft drop is a z cut. So this constraint here, this part here, is exactly the same as modifying mass drop. Now what you say here is that you're also going to keep things that are at small angles. So if this is your trimming radius, that's log 1 over r trim. The region to the right of this, smaller angles, is also going to be kept. All right? So that means that the region where you do veto emissions is this region above that line and to the right of this one. And again, there's three possible situations. Either your mass is above this, in which case what you do get is exactly the same as what you get for a plane jet mass. This constraint has no impact. Or your mass is somewhere in between these two regions here, in which case the constraint of the mass vetoing this region above a certain mass is exactly the same as what you would have had from modifying mass drop. Or there's a region where you're below, and if you're below, your Sudakov now becomes different and has an extra contribution compared to what you had for modifying mass drop. So for rho smaller, so this region here is going to be f trim times r trim over r squared. So if you get the mass of this, the mass that you have at this intersection, z is f trim and r is r trim, right? So that's and theta is r trim. So that's the value of the mass. For this region, you recover the same as modifying mass drop. And for rho smaller than this value, what you get is exponential of minus alpha s cr over 2 pi. You get log squared 1 over rho minus log squared f trim over rho. That would be the modifying mass drop region for this, and you need to add this triangle here, which is plus log squared of, and in that case I need to remember, I never remember exactly, I think it's f trim times r trim over r squared over rho. Again, no, this is obviously when rho is this transition point, you get 0, and then you get a log squared scale by the appropriate area of this guy. How is that interesting? This is actually easily shown. It means that if you look at a jet mass now, imagine this is the plane jet mass. Remember, modifying mass drop has a transition point when you hit this guy and where you do get something which decays slowly. That would have been modifying mass drop. So that's plane. That's MMDT. and that's a place which is Z cut. Now what we see is that for trimming, there's the same thing here. There's the same distribution with now the transition point being F trim, and at some point where you hit a transition point which is R trim over R squared times F trim, yeah, you get again another essentially double log kind of button. All right? In this case, which one do you like best? So trimming is great as long as you stay in this direction. In this region, there's, yeah, in this region, trimming and modified mass drop are give or take the same. There's subtleties. The effective radius is actually going to be the trimming radius, which is smaller than the effective radius you'll get from modified mass drop. So the sensitivity to non-perturbative effects is going to be reduced, slightly reduced, but give or take in terms of perturbative QCD, they're the same. Now, if you look, this can be dangerous. Imagine you're using this to make a bum hunt, okay? And you'd expect a bum to be somewhere in this area. Modeling your background with a kink right in the middle of your distribution can become a problem. So this is something you need to be aware of when you're using trimming. Be aware, watch out that you're not standing in this region. And at the moment, for the typical reach of the LHC, you're fine. If you take a jet which is something like, take higher G LHC, where you hope to get to a few TeVs, if you take a jet of 3 TeV, which might actually sometimes be not so ridiculous, if you take a 3 TeV jet, actually this falls right in the region of the W mass, or the Higgs mass, give or take. So for high energy, for now, this bump is low enough. If you crank up the PT, that might come and haunt you. So again, I don't necessarily want to advocate for modified mass drop in this region, but in this region, that's definitely something where I would say modified mass drop or soft drop avoids complications. In terms of QCD, the other thing with trimming is if you start essentially in this region down here, deep down in the resonation region, what you're effectively doing is you're getting a log, you're replacing your log of 1 over rho, log square of 1 over rho, with a log square. I'm actually missing some parentheses there to alpha SCR factor. You're replacing your log square of 1 over rho with a log square with a different scaling in the radius. So essentially replacing your jet radius with a trimming radius. But besides this, the structure is the same. So all the complications you had with soft and large angles and non-global logs, they will still be there. So in terms of perturbative QCD calculation, these effects are reduced. The scale with a smaller radius, soft and large angles are reduced, but they're still there, and so making precision calculations, in that case, that's definitely easier to do with modified mass drop. So to my knowledge, the only, say, measurement of the mass distribution has been done with, genuine measurement, unfolded from detector effects and things like that, that has been done with modified mass drop and soft drop, but not with trimming. Correct me if I'm wrong, and that might be the case. Yeah, I think I'm good. 2 minutes to make plans for next week. So there's one thing I haven't discussed. I had kept that in case I had some time, but as usual I don't. One thing I haven't discussed is in terms of tagging, say, W, Z, Higgs bosons, which is a clear case. I told you at the end what you want to do is make a combination of a two-prong finder, trimming and modified mass drop, and some shape. I might be tempted to discuss shapes. Again, in this language, you can essentially discuss shapes on a single Loon plane, and so discuss how they behave. So I might be tempted to do this, depending on the other things I like to discuss. And then I like to discuss all sorts of other applications. That includes a brief description of why do you think substructure can help in heavy ion collisions? Why do you think jet substructure can help in trying to constrain Monte Carlo, and particular part and shower Monte Carlo generators? Why is machine learning such a big trend in the substructure community? So describe this that's probably going to be the biggest part of the lecture. And then I'd like to discuss also some sort of QCD curiosities, like ZG measurements or things like that. So next week is probably going to be essentially covering more phenomenological aspect, except maybe for some QCD aspect, but next week is probably going to be more, say, QCD substructure beyond these listing methods and trying to understand them. So that's the plan for next week. And again, if there's anything that hasn't been, so next week is the last one. So that's your last chance to make requests. If there's anything you think I haven't spoken of or is not listed in what I just said, feel free to ask, and I'm happy to answer next week, or do my best to answer next week. So thanks, and see you next week. Oh, any questions?
I have a question comparing trimming and the other method. Do you get something with one or the other, or can they be complementary from the QCD point of view?
Yes and no. So from the QCD point of view, I think so the main issue with trimming is this idea of a transition point and the developed behavior. Now, the main issue with modifying mass drop, at least in this region, is the fact that imagine you have a jet where, I don't know, you do have something like this plus extra radiation everywhere. Modified mass drop is going to define two jets here, where the size of the jet is essentially this angle there. It's going to uncluster until you reach that angle, and you'll be left with two jets which have this size. So this means that essentially if this is an angle theta, you'll get some contribution from, say, pileup or underlying event, which goes like theta squared. Now, if you do trimming is going to draw a radius of size r trim around there. And so the contamination is going to go down from r squared to r trim squared. So the pileup and underlying event contribution is actually going to be smaller in trimming than in modifying mass drop. Now, this is the plus. Now, on the other hand, hadronization corrections go like 1 over theta and 1 over r. So hadronization corrections are going to go the opposite way, which is fine as long as you stay high enough in PT. But the minute you start getting closer to this region, that's not quite the case. The other thing is you can actually, so if you go back to the original paper, the mass drop paper by Gavin Salam, John Butterworth, Mathieu Rubin, and Aidan Davison, this one didn't just do mass drop. They were doing mass drop, and once they had the mass drop jet, they were actually doing some form of filtering, which is similar to trimming. So they were reclustering this with a smaller radius and keeping only a fraction of this, essentially keeping only 3 jets so as to capture both this and the potential extra gluon radiation. And so in terms of patching and avoiding this would actually do the trick. Discussing with some of the Atlas colleagues, apparently, essentially the phase space was not, both the phase space and the quality of the jet reconstruction at small angles, especially due to topo cluster in Atlas, was not good enough that this would make an impact. But apparently recent developments, in particular, I guess, with a particle flow that you would use in CMS, that can help. And this genuinely targets mitigating pileup effects. So in terms of mitigating pileup, even though trimming has this nicer property, you can probably get away with it by adding something onto the modified mass drop procedure. This is one idea, just doing some extra filtering. The other idea is to use something called recursive soft drop, where you would actually apply soft drop and carry on applying soft drop on each of the branches, which would in particular just remove do some extra grooming on the 2 prongs and effectively reduce this angle in the same way. So either doing recursive soft drop or doing filtering on top of this would solve the problem. And again, then some point when you really enter into the details there, you enter into the details not only of pilot, but also of the detector capabilities. And so this is, I know this is, well, the question of how to mitigate pilot in this case is always being discussed in the experiments. And whenever another method comes, it's always being discussed. So this is essentially the context. So I know some discussions are in place in both collaborations, but the exact status, I think it's still a bit premature. I guess the target is the end of the shutdown. Does that answer the question? More or less? Good.
Yeah.
Well, we can discuss it offline if there's anything extra. Anything else? Good. So enjoy the lunch break and see you hopefully next week.